It's quite likely that our technological civilization was the first of its kind on Earth. Still, what if that isn't the case? How certain are we, in fact? Join us as we delve into the research, examine the evidence, and ponder the implications of a pre-human civilization. Don't forget to subscribe and hit that bell icon to stay updated on all our cosmic adventures. Now let's dive into the Silurian hypothesis on Spaceverse. One popular method for estimating the total amount of life in the universe is the well-known Drake equation. This equation estimates the number of intelligent extraterrestrial civilizations that could coexist with Earth by multiplying a series of variables. These variables include the number of habitable planets, the likelihood of a planet forming life, the presence of technological life, and the duration of a civilization's existence. While the number of habitable planets in our galaxy has been determined to be in the billions, the remaining characteristics remain a mystery. That is due to the fact that our knowledge of how life and civilization originated is limited to a single instance. We are on pace to have at least one example of a technology species becoming extinct, but we have no evidence of any. We can instantly improve our estimate of the likelihood of any particular planet attaining that level of development if we find even a single more example of life or technology in the universe. However, do you know what would further raise the likelihood? Should we observe its occurrence on two separate planets? Two separate origins of life on Earth have been suggested by a very tenuous piece of evidence, if not proof at all, then at least a teaser of evidence. A Zorkin crystal discovered in Western Australia has a single carbon atom that appears to have passed through a living organism's metabolic filter. It has the typical greater ratio of carbon-12 to carbon-13 found in plant-exhaled carbon dioxide. That tiny bit of biogenic carbon was likely preserved in a Zorkin crystal for at least 4.5 billion years, long before the Earth's crust was likely reliquidified by a huge asteroid impact that should have killed off all life on the planet. Assuming the Earth resolidified between 3.5 and 3.8 billion years ago after its battering. The next oldest fossils, found in Australia and Greenland, date to that time. It's absurd to think that there are so many probability. In such case, the process of abiogenesis, the creation of life from inanimate matter, would have to have occurred once more. Under ideal circumstances, that would prove that life really does begin at the crack of dawn. If a suitable planet were to be found, we would need to revise our Drake equation estimate for the likelihood of life arising. Everything is highly conjectural, though, and the scarcity of these fossils is a major factor in the difficulty of establishing the beginning of life. Only that small portion of Western Australia and Greenland remain as visible land masses from that era. Tectonic action has pushed the entire remaining crust back into Earth's mantle several times, a process known as subduction. It is extremely challenging to trace the origins of life, since the crust is recycled around every 500 million years, erasing most of the early fossil record. But if Earth's geological history is as bad as it seems, our descendants in 500 million years will have very little proof of our existence. Would it be possible for us to realize that we are the planet's first technologically advanced culture? If we aren't the first, it will change our Drake equation in a big way. We'll have to reevaluate the chances of sophisticated civilizations emerging from life and how long we think those civilizations will last. A paper written a few years ago by Adam Frank, an astronomer, and Gavin Schmidt, a NASA climatologist, attempted to answer such an outlandish proposal. Their idea, known as the Silurian hypothesis, considers the possibility of the existence of industrial civilizations prior to the human race. The name is a nod to the classic Doctor Who series. Take skepticism about the existence of such a society seriously for a second. Such a culture couldn't have existed, according to Schmidt and Frank. There is no actual evidence to support such a claim at this time, and the burden of proof is enormous on the claimant. A very specific scientific inquiry is to be centered on an extremely conjectural notion. This is the true goal of both the film and the Silurian hypothesis. The overarching question is whether, in the absence of proof, a pre-human, non-human industrial civilization could have existed. Is that so? If so, at what point in time would it have had to have existed for it to have been entirely eradicated? And lastly, what remnants of such could we now seek out? Before we can even begin to imagine what our society may be like in the distant future, we need to have a good idea of what our ancestors may have left behind. Although our species has been for roughly 300,000 years, the Anthropocene period, which is defined as the era of our greatest impact, has only been in effect for the last 10,000 years. The 3 centuries or so after the Industrial Revolution have seen an exponential acceleration of that effect. Looking out at the world as it is right now, you could conclude that our buildings will be the most noticeable evidence of our presence once we pass away. That, however, will change soon. Though they may have endured for centuries, the pyramids certainly won't endure for millions. All of our magnificent cities will eventually crumble into dust, be buried or swept away, or become deserts. After that, they will be followed by ocean floors, vast sedimentary layers, mountains, and deserts once again. A lot of stuff will get subducted under the Earth's surface as tectonic plates move. If it ever does re-emerge, it will be transformed into new rock in the mantle, where its geological record will be nearly erased. Will there be any evidence of these works that can be seen in the far future? Anything older than 500 million years is essentially extinct due to the recycling of the mantle. The fossilized bones of prehistoric dinosaurs dating back hundreds of millions of years are, nonetheless, abundant. We should then expect to discover artifacts from a civilization that is barely a few thousand years old. However, given the possible spatial and temporal limitations of the civilization, such may not always be the case. In all likelihood, we have surface samples from Earth that date back millions of years. Most of the sites can only be accessed by excavating or drilling, while a few are still exposed. But here's the rub. Up until the Quaternary period, which began around 2.6 million years ago, we have only been able to access a small part of the original surface of the Earth. Contemporary metropolitan areas occupy less than 1% of the planet's surface. We highly doubt that we would have discovered any tangible artifacts from a society similar to ours a few million years ago. Not only fossils, but also cities and artifacts fall under this category, due to the extremely low fossilization rate. We have only found a tiny percentage of the total number of species that have ever lived. Keep in mind that between 240 and 65 million years ago, the Earth was inhabited by dinosaurs. A third of their time on this planet has passed since they left. We only have a small number of examples spanning that 180 million years. If we look at the fossil record side by side, our industrial age and the 10,000 years of human civilization are hardly noticeable, though T-Rexes in general are not hard to come by. Those dating back just a few centuries have proven elusive. I'll explain the scope of the Anthropocene blip by saying that sedimentary rocks are the best indicator of past epochs. Over millions of years, this rock was produced when various marine organisms' remains fell to the ocean floor. By analyzing layers of exposed sedimentary rock or deep cores dug from the oceans, we may trace changes in ocean chemistry, temperature, and biological composition. These effects are then reflected on a worldwide scale, in kilometers of sedimentary layers. The entire Anthropocene will be represented by a layer that is only a few centimeters deep. The industrial age will be a very minuscule part of that, maybe only a few millimeters thick. This extremely thin layer in the geological record may be identifiable to a society in the distant future, even though they would likely not locate any human remains or artifacts. We left a wider imprint as our cities and constructions expanded. The term Anthropocene describes the period of Earth's history when humans have had a profound impact on the planet's history. In all likelihood, it will soon become textbook material. Changes in the rock record over long periods of time are called geological eras. We can safely call this epoch the Anthropocene. Our actions are presently laying down a geological marker in fresh sedimentary layers that looks suspiciously like transitions in the record from millions of years ago. In order to determine if any of those past occurrences could be linked to industrialization, let's examine the details of the material that we intend to deposit onto the Earth's surface, which can already be seen in the recently formed sedimentary layers, in order to perplex geologists and paleontologists in the future. To start with, there are the obvious chemical and isotopic imbalances caused by all the strange stuff humans make. Heavy metals, chemicals, including CFCs, and their long-lived derivatives, and pesticides are examples of industrial pollution. Solid waste products from consumers, such as plastics and rare earth elements. Synthetic anabolic steroids and nitrogenous fertilizers used in industrial farming. The world's surface is covered in radioactive isotopes left over from nuclear bomb testing, which will remain for a very long time. Then there's the impact of habitat loss and species extinction, which will not appear as a separate layer in geological time, but rather as an abrupt decline in biodiversity indicators. Of all our geological impacts, climate change is the most significant. Do you recall the biogenic carbon particle in the Australian crystal? More than just specks, this is as a result of the Industrial Revolution. The air we breathe now contains around 500 billion tons of carbon, an isotope high in carbon-12. The atmosphere's C12 to C13 ratio is rising as a result, which is reflected in the ground, the water, and the sedimentary rocks that are now forming. The geological record will be impacted in several ways by the temperature rise linked to this additional atmospheric carbon. Rising sea levels and heavier precipitation both aggravate erosion. Ocean acidity rises as a result of increased dissolving CO2 in warmer waters, which in turn affects the kinds of marine life that can survive in these environments, and in the long run, the creatures that settle to the ocean floor. These are just a few of the numerous known and unknown impacts. As far as anyone can tell, our geological markings that read "we was here" will be easy for future civilizations to decipher. In such case, we ought to be able to track down an earlier one. Natural occurrences, however, can replicate a large number of these signals. Before we return to those natural answers, let's search for any intriguing geological markers from the past that resemble the one we're creating. Discovering technological civilizations that existed before humans is our mission. Several weird layers in our rock record may be evidence of huge environmental changes. For example, we know that an asteroid that hated dinosaurs crashed into Earth at the Cretaceous-Paleogene boundary. However, explanations for some of these are still not widely accepted. Finally, we reach the Silurian hypothesis, which speculates that an industrial society may have caused some of these unexplained sudden changes in the geological record. Schmidt and Frank zero in on two overarching categories that share many similarities. During the Eocene period, which lasted around 56–34 million years ago, we saw hyperthermals. Severe changes in carbon isotope ratios and sharp spikes in average global temperatures are hallmarks of these climatic events. According to the second theory, the quick injection of CO2 from burning some organic fuel is responsible for the temperature change. Is it possible that something similar to what we are doing could have sparked hyperthermals in the past? We are currently triggering one. Very much so, but brace yourself for the disproves. Then there are ocean anoxic occurrences which occurred on occasion during the early Jurassic and Cretaceous epochs. A dramatic reduction in ocean oxygen levels and an abundance of marine life extinctions are hallmarks of these events. A possible OAE is just getting its start right now. Similar to our situation, changes in CO2 isotopic ratios are frequently seen with ancient OAEs. Thus, climate change may have had a role in their initiation. Looking back even farther, a number of sudden changes involving MEHAs of the signals I've already mentioned have occurred since approximately 500 million years ago. As we delve deeper into the past, the precise reason becomes increasingly elusive, leaving us with greater leeway for our imaginative speculations regarding the rise of dinosaur empires. Natural climate shifts can mimic many of the present anthropogenic signals, including changes in temperature and carbon levels, as well as the different kinds of minerals being deposited on the ocean floor as a result of changes in marine life. This poses the greatest obstacle to evaluating the Silurian hypothesis. And there are a lot of natural things that could be causing the climate to change. One of these is the Milankovitch cycles, which are linked to previous climatic shifts and are caused by periodic changes in Earth's orbit. Additionally, a signal may have a common cause with climate change even if the two are not directly related. Technology production, or volcanic eruptions, which release large amounts of metals and minerals into the air and water, are two potential sources of spikes in rare earth elements and heavy metals. Possible causes of radioactive isotopes include neighboring supernova explosions or nuclear programs. Sedimentary soot and particle layers may be the result of massive wildfires, an asteroid strike, or the combustion processes of a long-gone industry. These have the potential to release particulate matter into space, where it can settle on Earth's surface. Furthermore, the release of sufficient CO2 has the potential to initiate a change in the climate. Solid evidence points to the intrusion of a massive magma zone over a massive fossil fuel bed as the primary source of the Paleocene-Eocene thermal maximum, the earliest and most intense hyperthermal event of the Eocene. Additionally, the kind of mass extinction that we anticipate occurring alongside our own geological bookend can be triggered by these kinds of disasters and the corresponding climatic change. However, human actions towards our own geological strata defy natural explanation in several ways. Industrial fluorides are just one example of a class of long-lived man-made compounds that have no recognized natural source. Some properties, such as the chirality of molecules, the degree to which their symmetry is left or right-handed, are strongly one-sided in nature, but appear to be completely at random when manufactured in industrial settings. Not to mention that previous climatic transitions seems to have been far less abrupt than the one we are seeing now. Therefore, it might be suggestive if the change happened over the course of a few centuries instead of thousands of years. That kind of temporal clarity, however, is very elusive in the geological record. As a whole, this raises an interesting paradox. A culture that vanished as a result of global warming would leave such a faint trail that it could be hard to detect. Conversely, a technologically advanced civilization that lives for thousands of years and is thus likely to have little impact on the environment would also be nearly undetectable. Regardless, differentiating between these man-made and natural circumstances calls for painstaking investigation into the setting, dispersion, and makeup of these marks as well as their relationships with one another, all the while assembling clues that may span entire geological periods. Has the presence of industry been identified in ancient geological transitions? Not at all. Our search, however, has been somewhat narrow. Schmidt and Frank agree that this is the main benefit of the Silurian theory. Our goal here is not to suggest that pre-industrial civilizations were responsible for past geological disasters. Rather, we are trying to better understand what signs to look for in order to discover such evidence. Even if it's highly improbable, finding such a pre-human society would have far-reaching consequences. If we want to know how numerous other civilizations there are in the cosmos and how we fit into it, we need to go beyond Earth. It can even help us find evidence of life in the past, including ancient Martian civilizations and other worlds. The most crucial thing is that finding a long-lost civilization that was just as advanced as us would show us how vulnerable we are and offer us a whole new outlook on our own destiny. We can perhaps learn from that hypothetical forerunner's mistakes and not end up like every other little geological blip that once hoped to explore the universe. As we wrap up our journey today, a big thank you for joining us at Spaceverse. Your support fuels our cosmic exploration. Don't forget to subscribe and hit the notification bell to keep exploring with us. Until our next cosmic encounter, see you.